Let's follow up the correlation idea in chapter 14 with this discussion on linear regression. So correlation, we were trying to come up with a measurement for the strength and direction of the linear relationship. And so we had the scatter plot, and we had some points put in here. And then we said, okay, let's estimate kind of that linear relationship with a straight line like this. Well, this straight line, the correlation was the measurement of how close those points fit to the line. So correlation was this ranking or this score of how close the points fall on the straight line. Okay, well then linear regression would be the process of coming up with the equation of the line. Need equation. And this line is what we call the best fit line. Best fit line. And really what we're trying to do is create the equation of the line that has the highest correlation. Okay, so there's a few things that we want to consider for this straight line. One, we want to consider that the generic equation for a straight line looks like this. Y is equal to some slope value times your x plus some intercept value. Okay, so here's the slope of the line, and here's your intercept value, the y-intercept value. So that's this point over here. Do it in yellow. How about red? Here's your a value, and then slope is just this measurement of kind of the angle of inclination of this line. Okay, so it makes sense if correlation is the measure of the line, and we have positive correlation means point up to the right, which also corresponds to positive slope. It makes sense that slope would be, if the line would be based on the correlation. Okay, so to figure this out, let's go to a new page and let's think about this. The correlation coefficient R was given as the sum of the products divided by the square root of the sum of squares of the x's times the sum of squares of the y. So we compute that, or we use the Excel command correl, or we use our calculators and run through this process. Okay. Sometimes calculators use SSXY to indicate the sum of the products, and they use SX and SY to indicate the sum of x's, sum of the squares of x's, sum of the squares for the y's. Just throwing that out there. In other words, they'll drop the first S and just write SX, SY, or SXY. Okay, so let's say we had our correlation coefficient R. Well, then we can create the value of the slope of that line by using this for B. Okay, so B is equal to, you could do it as the sum of the products over the sum of the x's, but I like it like this: the correlation coefficient multiplied by the variance of the y over the variance of the x's. And this is really nice because it allows us to kind of use the variability of the values themselves, not the combined values, but individually, and build up to kind of the slope. All right. Once we have the b value, if you think about it, and I'll go back to the graph that we have, the kind of balance point for any line is always going to be in the middle. So this balance point, which I kind of missed, but that's okay, and it's going to correspond to the mean values of the x's and the y's. So this balance point right there is always going to be found on a line, and it's going to be the average of the x's and the average of the y's, that ordered pair. Okay, that'll be always on our line. It has to be. We have to have some definite thing. So any best fit line is going to contain the ordered pair that comes from the averages, and then what we're going to do is roll or kind of tip the line about that point. Okay, and that tipping is going to be based on the correlation. So to come up with the value of that intercept, we're going to use this formula. So normally our lines look like this. If we had a point, I'll do mean x's and mean y, and we had a slope b, we can use the point slope form and say then it's going to be y minus y1 is equal to b times x minus x1. Sorry, I'm lying through my teeth here. There we go. And we can solve this for y. which would give us bx minus bmx plus my. Okay, so this part right here, that's our value a. So I'll write that up here. A is equal to the average of the y's minus the average of the x's times that correlation, or the slope of the line. Okay, so if you like, you can replace it with that. So let's run through an example, and then what I want to do is show you how to utilize Excel and kind of explain the features of the regression analysis on Excel to give you a sense of how it's useful to you, and just kind of to illustrate how you'll be seeing it. Okay, let's go through an example. Actually, I have an example up from our last video. Let's just use that one. Okay. So we computed these values. We had an ordered pair plotted for all ordered pairs, and we got this nice equation. Excel actually does a few things that are pretty nice. You can actually add a trend line, which is the best fit, and I'm not going to do that, but you could do that and just go ahead and put in a straight line. You can see that it put it in for us. What you'd want to do is display the equation on the chart and display the r squared value. So this right here, apparently I can't make it bigger. This right here would be the equation we're looking for, and this r squared was precisely the r squared from this correlation. Okay, but what I want to do is actually go through the process of finding the values a and b based on what we see here in Excel. So our equation, again, we're looking at this y equals bx plus a. B is going to be the correlation times the sx divided by the sy divided by the sx, and a is going to be equal to the average of, so mean y minus mean x times the b value. Okay, so let's compute the means and standard deviations for these. So I'll do the mean right here, x, and then y, and then I'll do the standard deviation for x and for y. Okay, so the average for these and the average for these. There we go, and then I'll do the standard deviation for the x's, and I'll do the standard deviation for the y's. Okay, so we have our correlation coefficient down here, r, and so the b value, I'm going to put it right here, the b is equal to the r value times the standard deviation for the y's divided by the standard deviation for the x's. Okay, and we get negative 1.3. If you think about this best fit line, well, there it is, the negative 1.3. Okay, so that'll tell us the slope of the line. Notice that the slope and the correlation aren't exactly the same thing, but correlation is definitely used to find slope. Let's find the a value. We're going to take the mean of the y's, and we're going to subtract the mean of the x's times the value we got for b, and there we go, the 5.9 right there. So if you like, you can just use the trend line feature in Excel, and it'll generate this stuff, and in fact it'll give you the correlation if you just take the square root of 0.4225 and then recognize that it has to be negative. Okay, or you can compute them directly, and then you can say, well, our equation then, y is equal to the negative 1.3 x plus the 5.95. That's nice. Okay, I'm going to steal these values and look at them in another sheet just by themselves. Okay, so the other nice feature about Excel is that you can run data analysis, and so with this option, previous Excel video kind of explores how to unlock data analysis. If you select this, what we want to do is run regression analysis. By the way, if you notice ANOVA single factor, you can do all of the stuff that I typed out on the other little document. You can do it with that feature, and it's lickety split, it's just done. Anyway, so here we go, regression analysis. Okay, and you say, okay, input the y range. Here we go. Input the x's. Okay, here we go. I did select the labels. Confidence level. If I wanted to test things at a certain significance level, I could specify 99%, which would correspond to an alpha of 0.01, and I'll show that in just a moment. And the output range, actually I want to keep it in the sheet, and I want to put it in right here. And that's it. I could kind of explore some of these other features, but I think that's a bit beyond what we actually need, so I'm going to leave these other parts off. Alright, and here it is, the summary output. Let's clean this up so you can actually see it. Coefficients, p-values. So here's some interesting things. It actually pumps out this regression statistic, so the multiple R, 0.65. That's something different than what we're looking at. Notice it's positive, but it's not supposed to be positive. The R squared, 0.4225. This part is coming from just the absolute value of variation explained, not the direction. So it's notice it doesn't say correlation, it just says multiple R. The R squared is the amount of variation explained in Y that's explained by X, and then you have the 8 observations. Okay, so what's interesting here is we have an ANOVA table output, and we could explore this, and the book does an okay job of kind of setting it up. But what's important here is that the ANOVA is telling us that this is the significance here is 0.08. Okay, so that's the p-value. So 8%. What is that meaning? Well, it's telling us that there's some things that just don't quite that aren't significant, and I'll explain that in just a moment. If you look down here, our coefficients, here's the intercept, the 5.95. Here's the, when it says x, what it means is the slope, and it's the negative 1.3. So it did the computations for us. It produced a standard error for these, right, because we're estimating these things, and so they have error built in. These t-statistics, again, you can look at the book to find out what these are coming from, but what's important is to note the p-values. Okay, so what this is doing, and what the ANOVA is doing, is testing to see if our coefficients here are actually different than 0. In other words, is the intercept different than 0? Is the negative 1.3 different than 0? If it's not, then what that's telling us is that the straight line that we put in could be anything. And in other words, it's kind of like a follow-up to the correlation, in the sense that these aren't actually correlated. There's no linear relationship between these two variables. But what's good about this is that we do see with the coefficient with x, this is the only one that really matters, it is 0.08. What is that telling us? It's telling us that it's not different than 0. It's not significantly different than 0. In other words, if we were to run a t-test on our correlation back here, we would see that that is not different than 0. Okay, we would fail our t-test, and it's really boiling down to having only 8 samples, and that you can look to our previous video to see why that's important. So if you increase the number of samples, or the number of observations, then it would become statistically significant. But we do see here that the 5.95 is different than 0. The p-value for that is less than 0.05, 0.01 even. And then here's some confidence intervals put out for those variables. So really, for us, we're just looking at the regression equation as a way to then predict something else. And what's important is to have this prediction show that the p-value being something less than 0.05 or 0.01, depending on how you set it up. We need that coefficient to be significantly different than 0. Otherwise, the regression line here doesn't really predict anything. Okay.